Okay, so test something out. Doesn't look like I have any current live viewers today. Hopefully I'll see the names pop up in the chat if anybody enters. But I'm gonna start doing these where as I record these, I'll also stream them live on a platform called Twitch, primarily used I think for like video gaming. But it's one way, and it's a little bit of a lag on the chat, but it's one way in which you could ask live questions. I probably will try to be taping these at the same times on Mondays and Tuesdays if we don't get through all the material on Monday. If you want to ask any questions, you're on here, please type something in the chat and I will try to answer it as soon as I see it pop up. Otherwise, I am going to include some more pictures as well as some board work. I've changed locations today, so bear with me a little bit. I don't have a huge whiteboard, but I do have one to write with I think is pretty sufficient. So last week we talked about confidence intervals, and some of the ideas that we use for confidence intervals will help us out with the next subject, which is hypothesis testing. Okay, so hypothesis testing, the basic thing of what we're trying to do is we have some proposition or some assumption about where the population parameter lies. Now, I'll quite often talk about this population parameter in terms of it being the mean, but it could be the population proportion as well. So we can do it for either one, but for starting out, I'll probably mention mostly the mean. So we developed some null alternative hypothesis about where this parameter lies. So the null alternative will be complements of each other. So if I assume that the mean is greater than or equal to some value, the alternative hypothesis would be that it's less than that value. Right? So they're going to be complements of each other. If we have enough evidence that goes against the null, right, or against that null hypothesis, which I also say is the assumed true value, if we have enough evidence that goes against that null, then we can reject it. If we don't have enough evidence, then we would not reject or fail to reject the null, right? We don't say that we accept it, we say that we fail to reject. So we just didn't find enough evidence in order to be able to reject it. So we failed to reject, but it's not the same as saying accept. So I'm going to use this motivating example as we kind of talk through what the null alternative and just the steps of hypothesis testing, which is, let's say we want to test this assumption or this statement that the average mass market beer has a lower ABV than Bell's Two Hearted, which has a 7% ABV. Right? So that's what we want to test. Right? We take a sample of 36 and we see that of those 36 mass market beers, the average is 4.5%. Right? So we wanted to test for whether or not the average mass market beer is lower than 7%, and we found some evidence that kind of supports that. Right? So can we say that in fact the true population, right? Because we only have a sample mean. So with this sample, can we say the true population mean is less than 7%? Right? What are the steps in order to make sure we can say that with a certain level of confidence? Okay. Well, we'll start out. Okay. We've got to come up with a null alternative hypothesis. What are we assuming is true, and what do we want to try to find evidence? Does the evidence go against that enough to where we can reject it? So the null is going to be this assumed true state of nature, or what we're going to assume is true, and if we can find enough evidence that goes against that, we can reject it. Right? So the alternative would just be the exact opposite, kind of a mention or a contradiction of that state, or the complement of whatever that assumption or that assumed state is for the null hypothesis. And we'll write these H subscript 0 and H subscript A for null hypothesis, H subscript 0, alternative hypothesis, H subscript A. Okay. All right. So we typically want to take whatever we found from our sample mean, or from our sample, that sample mean, and see if it's strong enough evidence that goes against the null, and if it's strong enough we can reject it. So we have kind of a couple different scenarios, right? Potentially, the sample evidence is inconsistent with the null, and inconsistent enough that we can reject it. Or the sample evidence is inconsistent, but not very inconsistent. This would be like saying, let's assume that the average mass market beer has an ABV of 7% or higher, and we find it 6.8. Well, yes, that's inconsistent with the null, but not very inconsistent, right? If the actual mean was 7%, well, it's fairly likely we could see a sample mean be 6.8, right? Because we know the sample means are normally distributed around wherever that true population mean is. And then the third kind of scenario is we just don't have enough evidence that goes against this null, or we actually find evidence that supports the null hypothesis, in which case we would quote unquote accept. I just didn't want to have a long enough area in my slide here to say we would fail to reject, right? Okay, so another good analogy of the way to think about these null alternative hypotheses are a court case example. So what are we trying to test when someone goes to court, right? Well, we're trying to find whether or not this person is guilty. Is the defendant guilty? Well, that's what we want to test for, right? So what do? We assume the exact opposite is true. So we develop the hypothesis that is this null, or the assumed true state of nature, which would be that you're innocent until proven guilty, right? The defendant is innocent unless we can find enough evidence that goes against that assumption, right? So if we assume they're innocent and we find enough evidence that supports they're guilty, then we reject the null, we reject that they're innocent, right? And you would go to jail. So the alternative there would be that the defendant is guilty, right? So you can kind of think about it as we're trying to find evidence that supports the alternative hypothesis, or does it go against the null enough to be able to reject that null? So if we have sufficient evidence to reject the null here, someone goes to jail, right? Right, with the assumed true state of nature, if we find enough evidence that that's not true, that means that the person isn't innocent and they go to jail. If they don't have enough evidence, right, then we can't reject that assumed true state of nature, the person is innocent, and you go free, right? The glove doesn't fit, you must quit, right? We failed to reject the null. That's a great, no, that's not a good pun. So we'll go back, right, with this kind of idea in mind, this court case example. Let's go back to actually how we work through a statistics example. So we've got the null alternative hypothesis. We're going to have three things we can test, right? So there's going to be three assumptions about the null, there's going to be three assumptions about the true population parameter, or the population mean, that we can make, okay? So the first is that true population mean is less than or equal to some value, right? The true population mean is less than or equal to some value, which in the alternative would mean that the population mean is greater than some value. So we'll name these tests based off of the alternative hypothesis. And this might make a little more sense as we kind of continue. But we base the name of the test off the alternative hypothesis. Okay? So if we want to test for that the mean is greater than a certain value, we assume the opposite is true, that it's less than or equal to that value. Similar idea, if we want to test for whether or not the population mean is less than a certain value, we assume that population mean is greater than or equal to that value. Okay? Oops. And then the last one we have, if we have that it's not equal to some value, right? The population mean is not equal to a specific value, we assume it is equal to that value and see if we can find enough evidence that goes against that. All right? So we call these first two one-sided tests and the last one a two-sided, right? Because here, the only way that we can find something that goes against the null hypothesis is if we find a sample mean that is in fact above this value. Here we can only find something that goes against the null if we find something that's below this value. But here, if we see a value on either side, right? If I assume that the population mean is 50, well, if I see 55 or I see 45, those both go against that null. But if I assume that the mean is greater than 50, well, 55 would actually support that null, while 45 would go against it. So that's why we have kind of one-sided, two-sided tests here. Okay? So there's kind of three steps that we'll use to kind of formulate these hypotheses. The first, what are we looking at? Right, we're looking at a mean or a proportion. That's pretty easy. The second, is it a one-sided or two-sided test? It's pretty easy. Look at the alternative hypothesis. If we have a greater than or less than sign in the alternative hypothesis, it's a one-sided test. If we have a not equal to sign, that's when we have a two-tailed. That's the only way we have a two-tailed test, in fact, is if we have a not equal to sign in that null hypothesis. Okay. So the third and final step, we have to decide where that sign of equality goes. Does it go in the null or alternative? And for us, what we're going to do, just like a kind of real easy way to remember this, is we always put it in the null hypothesis. So notice that equal sign is in the null hypothesis every time. And we'll end up seeing that it doesn't really matter, because when we're dealing with continuous variables, remember we said the probability of any one value is 0, and so that kind of equality doesn't end up really mattering a whole lot. But we'll always, just by convention for this class, always put it in that null hypothesis. Okay, so that's kind of what we're doing there. Let me see. I'm going to test something because I don't think anyone's watching this, but I want to make sure for future ones that we can make this work. So I created 2 accounts. Let's just double check that if someone does want to chat, okay, they can. That's my kind of other name. All right, so back to the motivating example where we're looking at ABV. Right? So what would our null and alternative hypothesis be here? So we wanted to test whether or not the average ABV is less than or lower than this Bell-Suharto, or 7%. Right? So in English, what we're trying to do is say, all right, we want to test for whether or not that ABV is lower than Bell-Suharto. So I'll assume the opposite is true. I'll assume that it's not lower than, or that it's greater than or equal to whatever the ABV is in Suharto. Well, using that actual number, right, what we're saying is, okay, I want to test for whether or not this average mass market beer has a population mean less than 7%. So I'll assume the opposite is true. I'll assume that it's greater than or equal to 7%. Right? So I've now got this one-sided test. Remember, the name of the test goes based off the alternative hypothesis, so we have a less than sign. So this is a less than or a left-tailed test. Right? If we had a greater than sign in the alternative, it would be a greater than or a right-tailed test. And if we had a not equal to sign, it would be a two-tailed test. But here we've got a less than sign, so we've got a left-tailed test. Right? So let's think about another type of example we could see, like an iClicker type question, or something you could see on an exam coming up, a potential exam coming up. Let's say we were given the following options, and we knew that an economist wanted to establish that the mean retirement age is different than 67. Okay, so anytime we see this word different than, right, that's what we want to test for. So if I take a sample, do I see any mean that's different from the value of 67? Well, if I see 70, it's different from 67, and if I see 63, it's different than 67. Right? So it doesn't matter which side I see that my sample mean be on of this, or value I want to test against. Both of them would go against it being equal to 67. So anytime we see this word different than, or just phrase different than, we should be thinking two-tailed test. And two-tailed test always means not equal to sign in that alternative hypothesis. So we have a not equals to sign in the alternative hypothesis anytime we want to know is it different than, right? Because direction doesn't matter there. If we find evidence on either side of that value of 67, it will be going against the null. Sure enough, if I want to test for whether or not it's different than 67 or not equal to 67, I assume the opposite is true, that it is equal to 67. And then from there, right, that's how I kind of identify that this is this guy. This is going to be my null alternative hypothesis. Okay. So we know how to kind of set these up now, at least in terms of identifying the null and alternative. So what are some things that could go wrong? Well, we'll talk about a few things, and then this will help us look at how do we work through an entire problem for hypothesis testing. Well, one of the biggest problems is we can make mistakes. Right? Just because I see a sample mean that's, goes against my null, well, it doesn't mean that in fact isn't true. For instance, if I assumed the mean is greater than or equal to 7% and the sample mean I see is 6.8, well, maybe I reject the null, but in fact the true mean was like 7.5, and yeah, I saw 6.8. It wasn't the most likely thing, but there still is some probability that I see that from a sample. Right? So we can make mistakes, and when we reject the null when we shouldn't have been, we'll call this a type 1 error. Right? If we fail to reject the null when in fact we should have been rejecting it, we'll call this a type 2 error. Right? So kind of this nice little table sets it up. Right? Anytime we reject it when in fact it wasn't true, that's good. If it is true, then we shouldn't be rejecting it, so those are correct decisions. But anytime I reject the null when in fact it's true, it's a type 1 error. And if I fail to reject it when in fact it's not true, I should have been rejecting it, that's a type 2 error. Okay? So I think here we've got kind of the same kind of table, but we're going to start saying, okay, these type 1 and type 2 errors, we're going to start calling this type 1 error alpha. Right? So alpha is going to represent the significance level that we want, Or eventually what we'll say is alpha is the probability, represents the probability that I'm making a type 1 error, okay? That I'm in fact rejecting when I shouldn't be, okay? And I'll try to give you a little kind of drawing here on the board in a second about this, but alpha is going to be when we reject when we shouldn't be, okay? So I've got a good representation here. Let's say we start out with the null hypothesis that someone's not pregnant, right? So we're trying to find enough evidence that we can reject that. Well, here would be a type 1 error, right? We reject the null that they're not pregnant and say you in fact are, when clearly this person can't be pregnant, right? So we're rejecting the null when we shouldn't have been. And here's a case where we're failing to reject the null. Remember, the null is that the person's not pregnant, so we're saying, yeah, that's true, we're failing to reject it, when in fact clearly you can see that null isn't true, right? So we got type 1, type 2 errors. It's kind of a goofy, easy way to kind of think about these with the pregnancy, right? So type 1 errors when we reject the null when it in fact is true. So we're going to call alpha this probability that we make a type 1 error, right? 1 minus alpha would be the probability that we don't make a type 1 error, right? So we can choose the probability, or we can choose the level of type 1 errors we want to make by selecting the alpha that we want, right? Usually we set this at benchmark values that are pretty low, 0.1, 0.05, 0.01, right? I'm only making type 1 errors 10% of the time, 5% of the time, 1% of the time, okay? So that's kind of, right? If I set the alpha at 0.05, then I'm rejecting the null when I shouldn't be 5% of the time, or I'm making mistakes 5% of the time, okay? So I'm going to kind of switch here, and bear with me. Let's get a little bit different setup than we've had. So I've got a whiteboard here. So if, all right, let's see if I can get this in here pretty good. So if we know that, say, if we took sample means, that they should be distributed around whatever the true population mean is. Well, we don't know what the population mean is, but we're assuming it's equal to a certain value. And just for the sake of this example, I'll keep using that ABV example, so we'll say 7%. Well, let's say that I do see a sample mean way out here, right, at 4.5%. Well, I could figure out, well, look, this is far enough away to where I'm going to reject that this is true. But if this in fact is true, then I'm making a type 1 error out here. So I know that any value that is out here, this far away from this assumed true mean, any value here, I'd be rejecting when in fact I shouldn't be. Or, because these are all the possible sample means I could see. So for 5% of these, they're going to go against the null, and I'm going to reject that null, but I shouldn't be, right? And how could I maybe know what this cutoff is? Well, if I know the area and the tail, I maybe could convert this into z-scores, right? I could maybe find what value would give me 0.05. I could find that z-score, which I believe it's like 1.65-ish. And then anytime I see something that's 1.65 standard deviations away from the mean, I'll be rejecting when in fact I shouldn't be. So you can kind of think about this area is going to represent alpha, or the type 1 errors that we're going to be making. Okay, so that should be good. Let's see if I can get that not to fall. So we've got these type 1 errors. Type 2 errors probably won't focus on quite as much in this course. A little bit more important, especially in kind of the hard sciences. I think that you probably focus a little more on them in your stats course. But they're inversely related to the number of, or the amount of type 1 errors you're making. So if I make more type 1 errors, I'd make fewer type 2. And how can I decrease the probability of making type 2 errors? If we select higher values for alpha, once again, they're inversely related. And then also if I took a larger sample size. So if I have kind of time there later this week, I might tape a little bit, kind of a little segment on type 2 errors, but we won't focus on it too much now. It's not going to be overly relevant to what we're doing. And then to kind of remember these type 1, type 2 errors, I usually like to use this at the end of a class, but here kind of fit in here. So, hey girl, I made a type 1 error. I shouldn't have rejected you, right? Because you rejected when you shouldn't have. That's a type 1 error. And still make the dad jokes even doing these online lectures, okay? Okay, so what are the full steps for conducting this hypothesis test? Well, is the sample evidence going to be inconsistent with my null? Well, first we have to figure out what this null is, and if in fact, if this null is true, determine where would the sample evidence be that would contradict it, right? So two approaches. We've got the p-value and critical value approach, so I'll probably cover both of them today. The first one, I'll go p-value approach, showing you how we do hypothesis tests for population means. And then I'll show you the critical value approach when we're doing hypothesis testing for population proportions. Now we can flip those. I could use the p-value or the critical value approach in either, and I'll try to make those kind of show you how they would lead to the same decisions, right? So let's go back to our example. We want to test this assertion that on average, mass market beers have a lower ABV than Bell's Two Hearted. So you know that Bell's Two Hearted has 7%, so we set up our null alternative. We kind of already talked about this. Now, I typically will write the alternative hypothesis as H subscript A. If you look in the book or you look at some other resources, you may see it sometimes written as H subscript 1. So I wanted to get this in here so we're aware it can be written either way. So we have a less than sign in our alternative hypothesis, which means we have a left tail or a less than test. Okay? So if in fact what we assume to be true is true, right? If this null hypothesis is true, then the true population mean is 7% or higher, right? So let's assume that that in fact was true. What would the distribution of sample means with a sample size of 36 look like, right? Well, we start out and we would have the true mean, let's assume it's 7%. Well, we could see 4.5, we could see 6.7, we could see all these different values, right? Now, for some of them, like these, well, these support the null, so for sure we won't reject the null if we find sample evidence that supports it. For this one, well, yes, this is evidence that goes against that assumed true value, but if I drew this to scale, it looks like it doesn't go against it very much, right? It still has a pretty high probability of seeing 6.7 if in fact the true mean was 7%. But seeing 4.5 looks like the probability we see 4.5 or something further, very, very low, right? So this is probably going to be one in which we would reject the null, this one probably not, and for sure we wouldn't with these because these are values, 8.5 and 9.5, that support the null. Okay? So, 4.5 and 7.9 are less likely to occur, but how unlikely, and I think here this wasn't supposed to be 7.9, let's say 6.8, I changed it, yeah, 6.7, somehow got those flipped up. So if we took a sample and found that 4.5% was that sample mean, can we reject this null? Or can we, are we failing to reject it? So how do we figure out how likely or unlikely it is and whether or not we're okay with that, right? Well, the first thing we'll do is we're going to convert, right, these sample means that we see into z-scores, or what we'll start calling z-statistics. Right? So how do we do this? Well, if I use that assumed true mean, right, I would know that in order to calculate a z-score, right, and this here, we'll go back to the board here. In order to calculate a z-score, what we've been doing before for sample means is drop my cat. So before, what we would do, all right, we say, okay, look, I've got this, and then the standard deviation of my sample means will be the square root of whatever the original variance was over my sample size, right? So then how do we find the z-score? We took whatever cutoff value we were interested in, right? Some sample mean here. We subtracted the population mean divided by the square root of here, right? Where that denominator represent the standard deviation of my sample means. Okay. Well, now the only thing that changes is I don't know the true population mean, but I have an assumed true population mean. So the only thing that changes is we calculate the z-score the same way, except for I have to use that assumed true value, which comes directly from my null hypothesis. So whatever value I have in my null hypothesis, that's going to be the value that I use to create my Z statistic. Okay. All right. So should know what all these things are. So once I have this test statistic, I then use, or this Z statistic, because it's coming from a standard normal distribution, right? In this scenario, where I know the population mean, I'm still using that standard normal distribution, so I'll call it a Z statistic, coming from that Z table. Right? So to get the p-value approach, right, I use whatever this assumed true mean is, and when I turn that sample mean into a Z statistic, or my test statistic, essentially what I do is I find the probability, right? Remember, what does a Z-score represent? It's the number of standard deviations away from the mean. So my test statistic would tell me the number of standard deviations away from the mean that I am. I'll draw something out here for a second. So we'll call this our Z-stat. All right, let's switch over here. So if we have that same drawing, right, what we could do is convert that sample mean we found into a test statistic or Z statistic. The p-value is the probability we saw that test statistic or something more extreme. Or said differently, remember the Z stat is just a Z value, so it's the number of standard deviations away that the sample mean I saw was from the assumed true mean. So if in fact this was the true mean, the probability I saw that sample mean or something further from that assumed true value, that's my p-value. Right? The probability I saw something this many standard deviations away from the mean, the assumed true mean, or more, that's my p-value. Okay. So this is going to be a little bit different. So the one that I drew was for a right-tailed test, right? The probability we see something that's greater than the assumed true mean. For a left-tailed test, it's going to be the probability we saw something less than that Z statistic. And for a two-tailed test, I always say it's essentially the probability you see something. If it's a positive test statistic, it's what's the probability I see something greater than it times 2. And if it's a left-tailed test, what's the probability I saw something less than my Z statistic times 2. Right? And so the reason why the two-tailed test is a little bit different, right, is because that's where we said evidence on either side was equally damning of that null hypothesis. So kind of draw what that would look like, right? So if we had a two-tailed test, and we said, okay, here's our sample mean distribution. I'm going to assume that the mean is, I don't know, let's do the, say 67 from the mean retirement age. If I saw 64, that would be the same as seeing 70, right? Both of these values are equally damning against the null. So let's say that I only saw 70. Well, I could turn this into my Z statistic. I could find the area to the right, or the probability I saw something that many standard deviations away or above. But for every value that I saw here, right, for every value I saw here, it was equally as likely I saw something that many standard deviations below the mean or further away in this direction. So if I find the 70 as my sample mean, I'll find the positive test statistic, I find the area to the right, and I multiply by 2, right, because there'd be two sides. If I saw 64 instead, well then I find the area to the left of that test statistic, but then it was equally as likely for me to see something above it, so I'd multiply by 2 as well. So for the two-tailed test, we kind of have this additional step, which is once we find that area, and the way I usually say it is that's more extreme than my test statistic, right? Because if it's negative test statistic, it was the area to the left. Positive test statistic, area to the right. Once I find that area, then I have to multiply by 2, because I kind of have two tails there with a two-tailed test. Very similar to confidence intervals, right? Okay, so we get this p-value approach. What do we do? Well, once we have this p-value, let me see. There we go. So here's kind of the left-tailed test, right-tailed, two-tailed. Right? So once I have this p-value, how do I make my rejection decision? Right? The whole point of this process is to be able to reject or fail to reject whatever that assumed true mean was. Okay? So the rule that we'll always use, and I'm going to say this a lot, I'm going to hammer it a lot, so you're going to get sick of it, but we always reject if the p-value is less than alpha. Right? So we'll always reject if the p-value is less than alpha. Okay? And essentially what that means is when we set alpha, we said that was the amount of type 1 errors we wanted to make. Right? Or think about it differently, it was if the probability of seeing the sample mean that we did was less than, say, 5%, then we're okay rejecting it. We're okay rejecting the null, right? If what I assume to be true, right, if I then took a sample and found that, okay, for this sample, the likelihood, if the assumed true value was in fact true, the likelihood that what I saw actually, what was the likelihood that I saw what I did? Well, if it's less than my 5% cutoff rate that I set, then I'm okay rejecting, right? Because it'd be so unlikely for the assumed true value to in fact be true, given that I saw this sample mean, then I'm okay rejecting the null, right? So when we choose this alpha value, this amount of type 1 errors we want to make, if the p-value is less than that, if the p-value kind of representing the probability I saw something this many standard deviations away from the assumed true mean or anything further from that assumed true mean, if that probability is less than this cutoff that of type 1 errors I'm going to make, then I'm okay rejecting. Right? That's just kind of a good way to think about it. So here's just line up all of our steps. Right? We'll determine the null alternative. That's important, right? Because we have to know the null alternative. We have to know, do we have a one or two-tailed test? We already saw that matters for the p-value approach. Specify what level of confidence or significance we want to test against, right? So if I think about my alphas of 0.01, 0.05, 0.1, those are significant levels of 1, 5, 10%, or said differently, confidence levels of 90, 95, 99%. Okay? We then calculate our test statistic. Using that test statistic, we find our p-value, and then if the p-value is less than alpha, we reject. If it's not less than alpha, we would fail to reject. Okay? So here's our approaches. Here's the steps to a p-value approach. Let's go return to our example and work through it. Right? So let's say I want to test this assertion that the average mass market beer, and I think I changed the name here, so I probably went back and forth. So ignore the beer name here, but we're still testing against that 7% ABV. We take a mass market, or 36 mass market beers in our sample. We find the sample mean of 4.5. Let's say we somehow know the population variance. Once again, this is a little fishy. We'll talk about what happens if we don't know it, but let's for some reason assume we know the population variance. Could we reject the null hypothesis at the 5% level, or an alpha of 0.05? Didn't really write this technically correct, right? Significance level of 5% or an alpha of 0.05. So what's the null alternative? We've already talked about this, right? We're wanting to test for whether or not it's less than 7, so we assume the opposite is true. That's greater than or equal to. Specify the alpha. We got alpha is 0.05 if we want the 5% significance level, or a confidence level of 95%. Calculate our test statistic. We know this is going to give us our z statistic, our z value. We use the assumed true mean coming from that null and alternative hypothesis of 7%, the sample mean we found of 4.5, and we get negative 15. So this is a pretty extreme example. I chose this for a reason to start out with. But if I saw this as a test statistic, what this is saying is, if what I assume to be true is in fact true, what I saw as my sample mean is 15 standard deviations away from that. Now we talked about, how many standard deviations away from the mean is far. Well, 2 or 3 starts to get pretty unlikely. So seeing something 15 standard deviations away from that would mean it's very unlikely that this is in fact the true population mean. Right? So we can compute the p-value. Now if we try to look this up in the table, we would want it's a left-tailed test, so we want the area to the left of that test statistic. It's going to be very small, right? Approximately 0, right? So like I said, if we go to that table, it only goes to -4. So anytime we see a test statistic more than 4 standard deviations away from the mean, the area to the left of that is going to be approximately 0, right? So if the p-value is approximately 0, can we reject or do we fail to reject? Well, we said we always reject if the p-value is less than alpha. So here with a p-value of approximately 0, it's going to be less than 0.05 pretty easily, right? So we'll definitely reject, okay? And then kind of adding this in, right? So I hate craft beer now because it's in. That was just a good hipster meme that I always trying to find a way to throw into the slides here. Okay, so one thing I wanted to kind of, so in the example where we had the assumed true mean of 7%, we found a sample mean of 4.5%. To find the probability that we saw that 4.5, given that the true mean actually was 7, we would turn that 4.5 into a test statistic, then find the area to the left of it since it's a left-tailed test, and that would be our p-value. So let's go to our next example and think about how we would solve this. So we had this one earlier where said a sociologist wants to establish the mean retirement age is greater than 67. Okay? So we want to test for whether or not it's greater than 67. So right away, if we're thinking about kind of our null alternative, that'd be the first thing we need to identify. Well, we want to test for, what we want to test for is the alternative. What you want to test against is the null. So here what we want to test for is that it's greater than 67. So we're saying the mean retirement age is greater than 67. That's our alternative hypothesis. Okay? So if we're writing this out, our alternative hypothesis is that it's greater than 67. We assume the exact opposite is true, right? That it's less than or equal to. So what type of tailed test do we have? Well, we have a greater than sign in the alternative hypothesis, so it's a right-tailed or greater than test. From there, oops, we take a sample of 25, find a sample mean of 71. So does that sample mean of 71 go against the null? Well, it sure does. We assume it was less than or equal to 67, 71 is greater. So it does go against the null, but does it go against the null enough? Well, that's why we have to figure out what the p-value is. Right? So next thing I need to do, calculate my test statistic. I've got my equation for the test statistic. The sample mean I found was 71. The assumed true mean that comes from my null alternative is 67. I was told the population variance is 81. That's something I would have to be given. And I had a sample size of 25. So once I plug those in, I get this test statistic of 2.22. Sorry if you can hear the dogs in the background. He's excited. So we've got this test statistic of 2.22. How can I find my p-value? Well, so go to my tables here real quick. Oh, wrong page, there we go. So I could look up, and I apologize, let's see it. There we go. You can see this a little bit better. So here's the 2.22, so I'll go 2.22, 0.9868 is going to be the area to the left of that, but and I'll subtract it from 1, right, to get the area to the right of 2.22, right? So here's my p-value of 0.0132. Okay. So do I reject or fail to reject? Well, if I go back, what level do we want to test against? I actually wasn't given one here. But what I can think about is what levels would I reject at? Well, with a p-value of, 0.0132, is that less than 0.1? Sure is. So if we only reject and the p-value is less than alpha, well, if it's less than 0.1, I would reject at the 10% significance level. It's less than 0.05, so I reject at the 5% significance level. But it's not quite less than 0.01, so I would fail to reject at the 1% significance level. Now, if I wanted to turn those significance levels into confidence, right, I would fail to reject at the 99% level, but I would reject at the 90 and 95. Okay? All right, so let's go through one more example. This one, I'm going to give you an example of a two-tailed, so it might be pretty easy to figure out what the null alternative is, me telling you that. But let's say some group says back to school spending averages is $606.40. Right? You don't really believe this, or you're skeptical, so you take a sample of 30 families and you find a sample mean that's a little bit higher, right? 622. You know somehow the population variance in school spending from historical data or something. So what would the null alternative hypothesis be? Okay. Well, if I'm just wanting to say whether or not it's different than this amount that the group stated, I just want to know, is the true mean something other than $606, or is it not equal to that value? So that's what I want to test for. I assume the opposite is true, that is, in fact, it is equal to that reported value. So, give me 1 second. Sorry, I thought the dog was getting into some food. All right, so we have the assumed true value of $606. And so if we look at the alternative hypothesis, not equal to sign, two-tailed test. Okay? So we got a two-tailed test. It's going to make things a little bit more difficult for us when we want to try to find the p-value. Okay? Now, first of all, if we go back here, when you're identifying the null alternative, one thing you should always be thinking about is whatever you find from your sample isn't going to be in that null alternative, right? Your sample is the evidence that you're using to either reject or fail to reject that null. So it shouldn't be the value in your null, right? So right away when you're given a little problem like this, whatever you see as your sample mean shouldn't be in that null or alternative hypothesis, okay? So what is the p-value for this hypothesis test? Well, remember, the p-value represents some type of probability, okay? So to see a probability over 1 doesn't make any sense. The p-value is a probability. We know probabilities have to be between 0 and 1. Okay? So what are the steps we need to follow? Well, we know it's a two-tailed test. So eventually we're going to have to multiply something by 2 at the end to find a p-value. But we have to start out first converting this sample mean into a test statistic. So in the example here we have an assumed true mean retirement age of 67, but we found a mean of 71. It's a right-tailed test, so the p-value is the probability we saw 71, given that 67 is in fact the true mean, or that we saw anything greater or anything further from that assumed true value of 67. So we turn 71 into this test statistic. We'll look the test statistic up in that standard normal distribution table. So we look up 2.22, right? We look up the 2.22 here. 2.22, 0.9868. So that's the area to the left, 1 the area to the right, so we subtract it from 1, and we're left with 0.0132 as our p-value. Well, we have the equation here. We just a matter of plugging things in, right? My sample mean was 622, the assumed true mean 606. I was given this population variance and my sample size. So I've got a test statistic of 1.39. So when we have the assumed true mean of 606 and we found a sample mean of 622, we turn that into our z, our test statistic, which was 1.39. But the area to the right of that, that's not our p-value. That's only half our p-value. Because for every value that we saw that was 1.39, 1.40, 1.41 standard deviations above the assumed true mean, it was equally as likely we saw something that many standard deviations below the assumed true mean that would have been equally as damning of evidence. So once we find the area in one of the tails, we know we have to multiply it by 2 in order to get the total p-value if we're dealing with a two-tailed test. If I go here, I look up 1.39, 1.3 all the way over 0.9177. But right, remember, 0.9177 by 2. So Once I subtract that 0.9177 from 1, that gave me the area on the right tail, multiply it by 2 to get the total area, and now I have my p-value. So what levels can I reject at with this p-value? Well, I only reject if the p-value is less than alpha. So is this p-value less than alpha? Well, 0.16 is not less than 0.1, it's not less than 0.05, and it's not less than 0.01. So I fail to reject at every single level. Right? And here's kind of a nice summary of that. Stop. All right, took a pause for the dog there. So, if we look at these, and we can say, well, could I reject these different levels? And I could look at any alphas I want. Here I did 0.2, 0.1, and 0.01, but I could replace 0.2 with 0.05, or whatever level I'm interested in. You can kind of see, when we have a lower p-value, where I kind of mentioned we can reject at high levels, but we fail to reject at these lower alpha values. For the second example, when it's a really high p-value, well, at the, here, if we're checking at, significance level of 20%, we could reject. But for levels of 10 and 1, we would fail to reject. And our conventional levels we usually test against are 10, 5, 1%, because they correspond to 90, 95, 99%, similar to when we're doing confidence intervals. Right? Okay, so for today I want to work through proportions as well and introduce to you the critical value approach. And then I'll likely kind of finish tomorrow's lecture up. We'll see how much time it takes me to get through this, but I'll likely finish up tomorrow. And I'll post another one where we do, when we don't know the population variance, how do we do hypothesis testing for sample means, and then kind of the walkthrough for Excel. Okay? So I've got, from trying to set up a null alternative hypothesis, if I'm doing this now instead of for means, I'm doing it for proportions. Right? I'm going to have a null alternative hypothesis still, nothing there changes. I still have 3 different types of tests, greater than, less than, not equal to. So right tail, left tail, two-tailed test. Okay? Nothing changes there. The only thing that changes is instead of the mean and the assumed true mean, I have a proportion and an assumed true proportion. Right? So nothing's really changed there. I've got one-side, two-side tests. The steps are exactly the same if I wanted to do the p-value approach. But if I want to do the critical value approach, the first 2 steps are the same, but then I've got something that changes. Right? So instead of finding a p-value and comparing that to alpha, for the critical value approach, I'll find a critical value and compare that to my test statistic, or my z-statistic. So how do I find these critical values? Well, depending on the type of test and what my significance level is, determines how I'll find this critical value and assign my rejection region. And I will talk about that in a second. But once I have that region, I then calculate my test statistic. Well, now here it's a little bit different because I'm combining now the critical value approach, but also we've kind of switched from population means to population proportions. So what changes? Well, just like before, it's the same exact equation we're using for our test statistic. It's just now I don't know the population proportion, so I have to use this assumed true proportion. Right? I'm assuming this is the true proportion, so I'm using that in my test statistic calculation. But other than that, it doesn't change from what we're doing with like confidence intervals per se. Okay? So slightly different equation for my z value or my z statistic. But once I have that, if that z statistic falls in my rejection region, I reject. If it's not in that rejection region, I fail to reject. Okay? So it becomes pretty clear what's important is where is this rejection region? Right? And I'll kind of mention, so here we're assuming that that value is the true population proportion. And so we know that if it was the true population proportion, that the variance would be a function of it, right? So I'll kind of, let's go here. So what we're doing with confidence intervals is a little bit different, right? Because we said with confidence intervals, all we had, well, actually, I don't even need to draw this. With the confidence intervals, all we had as a guess for where that population proportion was our sample, right? Now you can think about it when we're calculating this z-score, and we have this assumed true proportion. Well, I still want to be dividing by what that standard deviation would be, but I no longer have to use this approximation because I'm assuming that this is, in fact, the true population proportion, in which case I'm no longer using the sample, I'm using whatever that assumed true value is. So that's kind of where that comes from. So once we have that equation for our test statistic, now it's just a matter of determining, okay, how do I figure out, how do I assign this rejection region? How do I find my critical value? Well, the rejection region is going to be a region where if I see a test statistic that falls in it, I reject the null. It kind of separates, and the critical value separates this rejection region from the non-rejection region. And kind of this critical value is determined by what type of test I have and what level of confidence I want. Right? So kind of do a quick summary. And here I'm switching back to not using proportions, but what if I was doing this for sample means again? And the same thing would apply to proportions, right? I would just, instead of having sample means here, I'd have instead of having population means here, I'd have population proportions. So if I have a right-tailed test, the rejection region would be, okay, I determine my critical value, and anything to the right of it is my rejection region. So if I see a test statistic that's greater than my critical value, I reject. For a left-tailed test, I determine my critical value, anything to the left of it, or if I see a test statistic to the left of it, that's in the rejection region. For a two-tailed test, I'll find my critical value, and if the absolute value of my test statistic is greater than the absolute value of my critical value, then I'll reject. And in fact, if you want to follow this rule, so you don't have to worry about the signs here, you always reject if the absolute value of your test statistic is greater than the absolute value of your critical value. That way you don't have to worry about left-tailed, right-tailed in terms of signs. You just have to look at the absolute value. If the absolute value of your test statistic is greater than the absolute value of your critical value, you reject. If it's not, you fail to reject. Okay? So let's kind of talk about, let's see if I have a, So I'll go here first, and I'll kind of give you a little bit of drawing to determine, kind of figure out where these critical values come from. So here's kind of a nice layout summary. It's a little bit more kind of mathematical. Now, the way we find these critical values is it's the value, it's the z value that gives me whatever my desired alpha in the tail is. So I'm just going to draw this because I think it's a little bit easier than kind of walking through all the mathematics of that, greater than signs, less than signs. If I have, right, a left-tailed test, well then I know for that left-tailed test, anything that I see that's more than, if I want this alpha, let's say of 0.05, well, I can find what z value would give me that 0.05. So instead what we're going to say is this cutoff that gives me my desired alpha in that tail, that's my critical value. How can I find that? Well, if it's a standard normal distribution, I go to the middle of the table, I look up 0.05, and then go over, I go up to find what z value would give me 0.05 in the tail. So your critical value still is a z value, but it's more important that it's a z value that gives you the desired alpha in the tail. So a lot of times you'll see it as it's the critical value that gives you alpha in your tail. Now if it's a right-tailed test, right, well then only evidence on the right-hand side would go against the null. So now my critical value, I want, that gives me alpha in the upper tail. Right? Now if it's a two-tailed test, it becomes a little bit more difficult, right? So hopefully you can pause here if you need to write this down. But for a two-tailed test, well, alpha is the amount of type 1 errors we want to make. But we have two tails, so alpha is the total area in both tails. So if I've got half of alpha in each tail, my critical value will actually be when I look up half of alpha, right? So whatever alpha is for a two-tailed test, I have to divide it by 2 and then look at my critical value. But now I have two critical values, one's positive, one negative. So a lot of times we'll see this written as, right, the positive and negative, whatever that critical value is. Okay. So this is, like I said, a more detailed summary of that. Kind of notice I find the z value that gives me alpha in the tail for a right-tailed test. For a right-tailed test, oh, I already erased it. Well, for a right-tailed test, you can imagine, if we just had a right-tailed test, critical values will always be to the right or positive. Left-tailed test, they'll be negative. Two-tailed test, we said we had pairs. Okay? So, where's my rejection? Well, once I found those critical values, notice I kind of shaded the area in. That would be our rejection region. So if I saw anything in that shaded in area, if my test statistic fell anywhere in that area, we would say that we could reject the null hypothesis for that problem. Okay? All right, so nothing changes in terms of our test statistic. If we're looking at the means, what are critical values? I kind of already walked through this on the board, but let's say we had an actual alpha we cared about of like 0.05. Well, if I had a right-tailed test and I want 0.05 in that right tail, then I know the area to the left I want is 0.95. So I go to my table, I try to find the thing that's closest to 0.95. Looks like it's right in between here. So 1.6, whoops, 1.64 and 1.65, it's in between. So I take the higher of the two, 1.65, and that's going to be kind of my critical value for the 5% significance level for a right-tailed test. And now if my test statistic falls anywhere in this white region, right, this is because it's 1.65 standard deviations away from the assumed truth value or any further, my test statistic falls in here, then I'm okay rejecting. Right? If it doesn't, I fail to reject. So here's kind of a nice little summary. Left-tailed test, we find this critical value, the area to the left. This is our rejection region. So if our test statistic falls anywhere here, in this green area, I reject. For a right-tailed test, if my test statistic falls anywhere here, I reject. And for a two-tailed test, I have to compare it kind of to either side. Right? So I always draw these out just because I think plotting the critical value and then plotting my test statistic helps. And I'll show you some examples of this here in a second. So here's my steps, right? Determine the null alternative hypothesis, figure out what level of alpha you want to test against, or what your significance level is, calculate your test statistic, figure out your critical value and rejection region. You can flip 3 and 4, doesn't matter what order you do those in. Then once you have those, plot your critical value and rejection region, plot your test statistic. If your Z or test statistic is in that rejection region, you reject. If it's not, you fail to reject. So let's work through a few. Well, apparently I have my animations turned off here, so we already kind of know what the null alternative is going to be here. But let's talk through it. So you want to test the hypothesis for whether or not more than 50% of the population owns guns. So you want to test for that, right? That's going to be what you are testing for. That's your alternative hypothesis, or that the population proportion is greater than 50% or greater than a proportion of 0.5. You assume the opposite is true, right? That it's less than or equal to 0.5. So you've got a right-tailed test. Right? Okay, you then sample 100 people and find a sample proportion of 0.41. Right? Now, right off the bat, what should be our rejection decision? So a lot of times I like to ask this question when we're live, and the answer should be, well, look, I'm assuming, remember, take a step back. The null is that I'm assuming that this is true. Well, I found a sample proportion that actually supports this. I should be failing to reject the null, right? I should definitely not reject the null. I found evidence that supports it. But if we work through this problem, we'll see that even if we work through the entire problem, it would always tell us that, yes, in fact, you should not, right? You should fail to reject this. So we can still find critical values and things like that. So what would the critical values be for this test? Well, I've got them selected here, so it's a little bit of a spoiler. I guess my animations, I probably had these turned on. But for the 1, 5, and 10% level, here's my critical value. So why would these be my critical values? Well, if I think about, I've got a right-tailed test. So automatically, for a right-tailed test, I should be thinking about my critical values are on the right side or positive. Right? So right away, I know for a right-tailed test, only A and C make sense. I then want the values that give me these desired alphas in the right tail. So let's just say I look up the very first one, alpha of 0.01. Right? Remember, alpha is the area you want in the tail. So when I go to this table, the area I want in this tail is 0.01, but it's a right-tailed test. Well, these represent the areas to the left. So if I want 0.01 in the right tail, then to the left I have 0.99. So I find what's closest to 0.99. In between these two, 2.32 and 2.33. So take the higher of the two, 2.33. Okay, I could look up the other two, but that helps me identify that this is going to be the correct one. Right? Now, I should always find the same three values. If I have the same type of test and same levels of alpha, I'm going to always find 2.33, 1.65, and 1.29 for this right-tailed test when I'm looking at a proportion example. Okay. Now these would look like critical values for a two-tailed test where we have pairs, right, of critical values. Here's what it would be if we had a left-tailed test, right, the same values but negative, right? And these are just wrong. Right? I believe these would be if I had a two-tailed test, but I didn't identify I actually have pairs for a two-tailed test. Okay. All right, so we'll go back here. So what if I want to find the test statistic? Well, if we're looking at these, right away we could rule out A and D. Why can we do that? Well, remember, we're assuming the population proportion is 0.5. We found something below that. So if we look at our equation to calculate this test statistic, we take the sample proportion minus the assumed true proportion. So if we found 0.41 and this is 0.5, our test statistic should be negative. And you can ignore this guy right here. I'll delete that and repost the slides. I don't know why I have that in there. I think it's because that's what we want to compare this test statistic against. But so we calculate this test statistic, plug in our values that we have, 0.5, 0.41, and 100. We get negative 1.8. Because we found sample evidence below the assumed true mean. So I have a question on Twitch. So yes, we're going to have another iClicker kind of question, kind of weekly quiz this week, but it'll be based off of this week's lectures, right? So off today's and then off of the one I get posted tomorrow as well. Okay. So I'm glad somebody tried to use this this platform of Twitch to ask questions. I appreciate that. So what's the p-value for this test? Well, if we wanted to look this up, we've now got our test statistic of negative 1.8. The p-value would be for a right-tailed test, the area to the right of that. So what would I do? I would look up negative 1.8 in my table. Right? So I go ahead, I look up negative 1.80, 0.0359, but that's the area to the left. I have a right-tailed test, so I'd have to subtract that from 1. When I subtract that from 1, I get 0.9642. Okay? Now clearly at this p-value, is this going to be less than any alpha? Definitely not, right? This isn't less than 0.1, 0.05, or 0.01, so we fail to reject at every level, which is what we originally said we should do because this sample evidence supported that null hypothesis. So for this one, it's fairly easy because when we had a test statistic of negative 1.8, when we drew out our rejection regions, right, these three critical values that went with the 90, 95, 99% confidence levels were alphas of 0.1, 0.05, and 0.01, we can clearly see negative 1.8 isn't even close to being in those rejection regions. There we go. If instead I'd found 1.8, what would that look like? Well, I still have the same three critical values because I still have the same type of test. I still have the same three alphas, right? So I've got 1.29, 1.65, and 2.33. Here's my rejection regions. Where would 1.8 be? Well, I plot that test statistic of 1.8. It's in the rejection region for the 90% level, or the significance level of 10%, or an alpha of 0.1. It's in the rejection at the 95% level, or 5% significance level, or an alpha of 0.05. But it's not in that rejection region, right? For, and this is 2.33. It's not in the rejection at the 99% confidence level, 1% significance level, or alpha of 0.01. So we reject at the 90 and 95%. If our test statistic was positive 1.8, we would fail to reject at the 99% level. Okay? So that's how we would work through kind of an example with proportions. Kind of a nice summary slide here. Right? We fail to reject at every single level, whether or not we use the p-value or the critical value approach. It doesn't matter there. Okay? All right. So since I know I have one person on there, I'll pause and see if anybody has any questions before we kind of keep moving from this example. I know there's a slight delay, so I'll pause for a few seconds. Okay. So the second example we're gonna use is a smoking example while pregnant. So we worked this one in class. Once again, I have these for the complete version of the slides. I forgot to turn all my animations on, so we're always gonna know the answer, but we can at least walk through why the answer is what it is. So let's say you want to test against the hypothesis that less than 15% of Indiana mothers smoke while pregnant. So up to this point, I've always set these up as what you want to test for. So what you want to test for is the alternative. What you want to test against is the null. So here, if I state what I want to test against, then my null is actually that it's less than or equal to 15%. So my null here is that that population portion is less than or equal to 15% because that's what I'm testing against. Right? I take a sample of 400 mothers, I find 72 smoked. So if I didn't give you the sample proportion here, you could have found it, because if I take a sample of 400 and 72 of those mothers smoked while pregnant, well then to get that sample proportion, it would be 72 over 400, giving me that sample proportion of 0.18. Okay? So here's my null and alternative hypothesis. I have a greater than sign in my alternative, so I have a right-tailed test. Right? So I should automatically know my critical value should be what? Well, if it's a right-tailed test, we just worked through one similar, they have to be positive. Right? Now, if I want to look at the same three alpha values, well, I'm going to find, if I look up the same area in the tail, I'm always going to find the same z value that gives me that. So I have the exact same three critical values. Right? Because we're using the same alphas every time, these kind of benchmark, 0.01, 0.05, 0.1, I'm always going to find the same three critical values. Okay? So I've got these three critical values. What's the next thing I need? Well, I can plot my kind of rejection regions, right? And then does my test statistic fall in those rejection regions? So I'll show you a picture of this in a second. But first, how do I calculate my test statistic? Well, we've got this equation for my test statistic here. Take the sample portion minus the assumed true portion. So 0.18 minus 0.15. Plug in the 0.15 kind of here and here. This should not be 0.2 and 0.8. This should be, I apologize, this should be, what's wrong with this? Okay, let me change this real quick so that the numbers line up. I think I probably copied and pasted a little bit too quick there. Where are you? There you go. So this should be what? 0.15, and then 0.85. And I believe these numbers are correct, but for some reason I didn't have that updated in there. Okay. So get the correct numbers plugged in there now. And this was 1 minus 0.15. So I get this test statistic of 1.68. So for this example, we have the assumed true proportion of 0.15, and we find a sample proportion of 0.18. If we turn that into our test statistic, we see that's 1.68. And if we plot that against our three rejection regions, we can clearly see that it's in the rejection region at the alpha of 0.05 or 95% confidence level. It's in the rejection region for the alpha of 0.1 or 90% confidence level, but it's not in the rejection region for the alpha of 0.01 or the 99% level. So we rejected the 90, 95, but not the 99% level. There we go. So we've got our critical values, our test statistic. It kind of showed you when we plot against this, we end up rejecting at 5 or 10%, but not the 1% level. Okay. I think what I'm going to do is kind of take a break today. Tomorrow, we don't have a ton of slides left to go over, but we'll walk through a few examples of when we have a population mean, and we're taking a sample, but we only have a sample variance. We don't have the known population variance. Now, one thing I wanted to kind of go through as well shows a few more pictures though before we end for today. My cursor, right? So, and also I think I can zoom in a little bit. So there we go. So here, right, there we go. So notice if I'm looking at these, once I turn these into a z statistic, once I turn my sample mean into a z statistic, whatever z or test statistic I find, well, the area to the right of it for a right-tailed test, I said that represented my p-value. To find the critical value for a right-tailed test, I knew that it was whatever gives me alpha in that right tail. So kind of notice this black shaded area, or where I kind of drew this area where alpha is. Well, that's alpha is the area of my tail, and the critical value was just the z value that gave me alpha in that tail. Now the test statistic for a right-tailed test, the area to the right of my test statistic, that area just represented my p-value. So notice, anytime my p-value is smaller than alpha, right, this red area is p-value, if it's less than the shaded black area of alpha, I reject. But notice if the test statistic, if my p-value is less than that chosen alpha, it would have to be for a test statistic that is somewhere to the right of my critical value. If it's somewhere to the right of my critical value, then what that's saying is the test statistic is larger in absolute value than my critical value. Right? So if the p-value is less than alpha, my test statistic has to be greater than my critical value. If my test statistic ever went outside that rejection region, so over here, well, now the area to the right of my test statistic would be a p-value that is larger than alpha. And I have the same thing drawn out for a left-tailed test. And here's where, in order to kind of avoid using this less than, greater than, notice if I had, so this is a scenario I drew where the test statistic is in fact kind of less than, in absolute value, it's less than my critical value, or it's outside my rejection region. Well, once it's outside my rejection region, notice the area to the left for a left-tailed test, the area to the left of my test statistic represents my p-value. So now my p-value is going to be greater than that desired alpha, so I would fail to reject. So the p-value is greater than my alpha, I fail to reject, and it would have to be that my test statistic is then pushed to be outside of that rejection region. So that we're always going to make the same decisions, and that's because the p-value is explicitly linked to that test statistic, and alpha is explicitly linked to that critical value. So I'll talk through a little bit more of this tomorrow. We'll work through a few more examples where we have a sample mean, and we want to figure out if we can reject certain values for the population mean when we only have the sample variance. So just like confidence intervals, that means we're going to have to go back to using the student t distributions or that student t table. So I'll be looking, kind of using that tomorrow as well, and then walking through an example for each type in the Excel, which will then give you what you need to kind of finish that Excel assignment. Okay. All right. So I believe your Connect homework's due tomorrow. It's kind of, they're a little bit older material, so they don't have any of this hypothesis testing stuff on there. So you should be able to complete those by the end of the day tomorrow. If you have any questions, I've had a few of you send me some emails, but I'll be trying to check my emails a little bit tonight and then all day tomorrow as well. Okay. As I mentioned, if you want to sign on again at 10:30 tomorrow, we'll be here streaming, but that ends today's lecture.